Hi there, Miss Barber here. Let's get started. Example 1. Sketch a graph of f of x equals 1/3 x cubed minus 1/2 x squared minus 2x plus 3. Following the guidelines provided at the beginning of this section of notes, we'll start by looking for the domain. Since f of x is a polynomial function, we know that the domain is the set of reals. How about intercepts? I'll begin by looking for the y-intercept. The y-intercept occurs where x equals 0. So if you put in 0 for all x values, you get the constant 3 remaining. We have a y-intercept at the ordered pair 0, 3. I'm not inclined to look for the x-intercept or intercepts because that's a whole lot of work. How about if we look for symmetries? Is the function even? If it's even, f prime of minus x would equal f of x. And if it's odd, f prime of minus x would equal minus f of x. You can compute these on your own time, but you will soon see that this function is neither even nor odd. Now how about asymptotes? Since this is a polynomial function, we know that we're not going to have any asymptotes at all, so we'll have none. But in behavior, that's something interesting to look at. If you recall from your pre-calculus classes, you might remember that a polynomial function of odd degree, this is degree 3, with a positive leading coefficient has in behavior such that in the third quadrant, the function will continue to go towards negative infinity, and in the first quadrant, the function will move towards positive infinity. We write this in our calculus class as the limit as x approaches negative infinity of the function f of x, that's negative infinity, and the limit as x approaches positive infinity of f of x, that goes to positive infinity. We'll continue with the first derivative test. The first derivative test can be used to find the local extrema and also define intervals of increase and decrease. Regardless of the derivative test you choose, the first derivative test or the second derivative test, we begin by finding the critical values. Critical values are where the first derivative equals 0 or where the first derivative does not exist. Let's begin by finding the derivative. For the function f of x equals 1/3 x cubed minus 1/2 x squared minus 2x plus 3. The first derivative, f prime of x. For 1/3 x cubed, bring the 3 down and multiply it to the 1/3. That'll give you a coefficient of 1, so we just write x to the power of 3 minus 1 would be x squared minus the derivative of 1/2 x squared. 1/2 times the power of 2 when brought down is just 1. So you'll have x, and then 2 minus 1. We don't write a power of 1. The derivative of minus 2x is negative 2, and the derivative of the constant 3 is 0. Let's continue. We can factor the x squared minus x minus 2 into a product of two binomials. That could be x minus 2 times x plus 1. If we set this equal to 0, as we need to, we would have 0 is equal to x minus 2 times x plus 1, and when solved, we would have critical values of x equals negative 1 and x equals 2. Let's observe that we don't have to be concerned with where the derivative does not exist because the derivative is also a polynomial function. Now, let's draw a sign chart number line for the first derivative. We'll begin by putting a number line, and I'll write f prime for the derivative slightly above the line and x for slightly below. Now let's mark the critical values. I'll start with when x is negative 1, the derivative is 0. That's what we solve for. And when x is positive 2, the derivative is also 0. Now we're going to look for the signs for each of the three regions. I'll begin by picking a number between -1 and 2, like 0. If we evaluate the derivative at 0, you're going to get 0 minus 2, that's a negative, times 0 plus 1, that's a positive. The product of a positive and a negative, well, that's negative. Now let's pick a number less than -1, like -2, and evaluate that number for the sign in the first derivative. -2 minus 2, that's a negative number. -2 plus 1 is also negative. The product of two negatives, that's a positive. Let's do that for a number to the right of the number 2. For example, I'll pick 3. Both 3 minus 2 and 3 plus 1 are positive numbers. The product of two positives, that gives us a positive. Now, looking at the sign chart of the first derivative to determine the behavior of the function, we see that the derivative is positive from -infinity to -1. That tells us that the graph is going to be rising. It's also rising again from 2 to positive infinity. And so we say that the function f, not the derivative, but the function f, is increasing on -infinity to -1 unioned with 2 to positive infinity. Between -1 and 2, the derivative is negative. If the derivative is negative, the graph would be falling. And so we say that f, the function, is decreasing in that middle interval. So it would be decreasing from -1 to positive 2. Keeping this in mind, at -1, the graph rises to it and then falls afterwards. So this looks like a high point. And we would say that f has a local max at -1, f of -1. And at 2, the graph falls to 2 and then rises again. So that point would be a local minimum. We would say that f has a local minimum of 2, f of 2. Let's go ahead and compute f of -1. f of -1 evaluated in the function 1/3 and then put in -1 cubed minus 1/2 -1 squared minus 2 times -1 plus 3 gives us the fraction 25/6. And for f of 2, evaluated in the function 1/3 2 cubed minus 1/2 2 squared minus 2 times 2 plus 3, that gives us the output of -1/3. We'll need those ordered pairs when we graph our function. We use the second derivative to determine concavity. We previously obtained the first derivative, which was f prime of x equals x squared minus x minus 2. Now let's get to the second derivative, f double prime of x. That's equal to the derivative of x squared, which is 2x, minus the derivative of x is just 1, and the derivative of -2 is a constant, so it's a 0. We now proceed to find candidates for inflection points. Inflection points occur where the second derivative equals 0 or where the second derivative does not exist. Let's proceed by setting the second derivative equal to 0. That is, 0 is equal to 2x minus 1. Solve for x. We'll add 1 to both sides. You get 1. equals 2x, and finally solving for x, you'll get x equals 1/2. Since the second derivative is a polynomial, and more specifically a linear function, we know that there will be no place for which the second derivative does not exist. Using that candidate x equals 1/2, let's make a sign chart number line of the second derivative to determine concavity. I'll write f double prime above the number line and x below it. I'll indicate that when x is 1/2, the second derivative is 0. Now we have two regions. We'll pick numbers in each of the regions and evaluate that number in the second derivative for the sign. A number less than 1/2, I'd pick 0. And so if we do 2 times 0 minus 1, that's 0 minus 1, that's a negative. Pick a number greater than 1/2. 1's an easy number to compute. So 2 times 1 minus 1, that's a positive. Knowing that a negative in a region for the second derivative tells us we have concave down. So for values less than 1/2, the graph is concave down. And then to the right of 1/2, the second derivative is positive, so it's concave up. We can write f is concave up on the interval from 1/2 to positive infinity, and f is concave down on the interval from negative infinity to 1/2. Since concavity changes directions at 1/2, f has an inflection point that is 1/2 f of 1/2. Let's go ahead and note that if we wanted the value of f of 1/2, which we will need to plot points, compute f of 1/2 in the original function, and that output will give you 23/12. Finally, we have sufficient information to get a pretty accurate sketch of the function f of x equals 1/3 x cubed minus 1/2 x squared minus 2x plus 3. For the xy plane, let's go ahead and mark the horizontal as the x-axis and the vertical as the y-axis, and we'll mark key values that we computed. First, let's mark the y-intercept of 3. Let's mark the local maximum we obtain using the first derivative, which was -1, and the y value we computed is 25/6. Let's go ahead from the first derivative again, mark the local minimum, which we marked at 2, and that ordered pair is 2, -1/3. We also computed a point of inflection. That point of inflection, again, I'm eyeballing quite a bit of this. This is where concavity changes from concave down to concave up. That ordered pair was 1/2, and the corresponding y value, 23/12. Now let's remember what the concavity was. It was concave down to about 1/2 and concave up afterwards, so we'll make a graph fit. It's going to rise from the third quadrant to the max. We'll go through, and notice we're doing concave down. We'll go through the y-intercept of 3, and very subtly, it's going to change concavity at x equals 1/2 from concave down to concave up, and we'll go all the way down to the min, and then the graph rises again. You can see if your calculator is correct by checking the output with the graph you just obtained.